Okay, so today we're going to talk about fractals, and hopefully you guys have had a chance to look at the Mandelbrot TED Talk that I sent you guys and read the paper. So the term fractal was coined by Mandelbrot, so by the speaker that you guys saw in the TED Talk, and he used it to describe objects that basically have two fundamental properties. They have the property of self-similarity and a fractional dimension. We're going to go today a little bit in more detail about what these two properties mean and what does that mean for the other properties that these types of objects called fractals exhibit. So looking at the first one, when Mandelbrot described self-similarity, he said a fragmented shape that can be divided in parts, each of which is a reduced copy of the whole. So in other words, there is this identical motifs that repeat in this geographical figure at ever-reducing scales, and that sort of brings this property of self-similarity. And he went over some examples of self-similar objects that we see in nature. Of course, what we see, if we see objects that are fractal-like in nature, they're only fractal-like or self-similar up to a certain dimension. So, for example, if we look at something like the lung, you see these tree-like branches that sort of, if you zoom in these branches, the figure repeats itself, and it's the same sort of type of tree-like branch structure at smaller and smaller dimension. At some point that breaks down, but it's still very interesting. There are all kinds of other types of phenomena in nature that again exhibit this sort of. These are images from Google Earth and in different parts of the world, and so you see again this sort of tree-like or a rough, as he called it. He talked about this property of roughness, right, in his talk, rough surfaces. And if you take one of these surfaces, for example, here in Saudi Arabia, and you zoom in, it's almost like you again see the same surface. You zoom in, you again. So maybe these type of fractal-like shapes in nature aren't quite exactly self-similar. They're almost self-similar, and we're going to talk more about what that means for mathematical shapes. So for the mathematical fractals, but an interesting property is that if you keep zooming in, you are not able to tell anymore where exactly am I. I'm not able to tell with my naked eye. Am I in the part of the system? How deep am I in the system? Do I see the whole system? Do I see half of the system? Do I only see a tiny, tiny fraction of the system? You're not able to tell that because everything just looks the same. So, for example, we have stock market data on the y-axis, and if I ask you what do you think is the x-axis here? Is it stock market data over what range of time? Who thinks it's minutes, for example? Who thinks it's days?
Definitely days.
Definitely days.
Yeah.
Who thinks it's years?
I go for days.
You guys are wrong.
Obviously. So this is a type of example where you have this self-similarity across different time dimensions, because really if someone just gives you this plot, you're not able to say, is it seconds? Is it minutes? Is it days? Is it weeks? Is it years? You're not able to say that. So for example, if we look at stock market data over different sort of time periods, they each exhibit these irregular types of shapes going up and down, but if I deleted sort of the x-axis here and what these represented, you would not be able to tell me like the time dimension here. And we saw the same thing for the space dimension here.
So the answer was years? The bottom one's the one that shows, right?
Yeah. So for example, if we go space dimension, like how big do you think this object, this little pin here is? because again, we see this sort of, this now in space, not in time. So we see this, this landscape made out of rocks. And as you zoom in, it's very hard to say, you know, how many people think it's like this big, for example. Or it could be this big. Or it could be, you know, this big. Like, can you tell? Can someone, like, what's your best guess here?
We're guessing the size
Of this little pin here.
It looks like a lens cap.
Yeah.
So how
Trick
big?
question.
Yeah, but I think it's huge. I think I'm being bait.
It's like, maybe this big. Okay, maybe this big. Let's look. Here's like the actual photograph now. It's pretty cool. So these are just some examples, these fun examples of these. This could be a very small room. Yeah. That's an assumption we make. Everywhere in mathematics we have these assumptions. We're assuming that man isn't very small, so the pin must be quite big. So this, one of my favorite things about this property of self-similarity is the fact that it speaks of a certain efficiency. It makes these objects incredibly efficient. So if we go back and we look at the lung, so when you have the lung, oxygen molecules are absorbed by red blood cells only when they come in contact with the lung wall, so with the wall of the lung. So here you have, in order for you to take as much advantage of oxygen as possible, you have to have a very high surface area. And so you have a structure like the lung, which is sort of in quite a small volume area, or other structures that have, you know, they can be encompassed in small places in space. But however, they exhibit these incredible lengths in maybe other dimensions. So here, the lung, because of it has this packing efficiency all over and can pack so much surface area into this tiny space, leads us to believe that maybe when it comes to these types of surfaces, it would be interesting to look and study their dimensions, not necessarily just looking at the volume of the space they occupy. Maybe it would be necessary to have other different type of dimensions associated with them. So Mandelbrot also looked at sort of trying to understand dimensions for these types of fractal objects, and that brings us to the second part of what I mentioned a fractal is, which is an object with a fractional dimension, and we're going to talk about that today. So before that, I wanted us, if you could take your laptops out, we're going to have a small exercise. And if you could type openstreetmap.org in it. And we're going to try to work in groups of maybe 2 or 3, so pick a partner. And what Mandelbrot observed in openstreetmap.org. So in 1967, Mandelbrot published this paper that's called "How Long is the Coast of England? Statistical Self-Similarity and Fractional Dimension." So he used the coast of England in this paper as an example of showing how types of objects like coasts, which could have fraction-like appearances, fraction-like properties, can have a longer length the smaller the size of the object with which we measure them is. So if we increase, for example, if we have a ruler and we try to measure the coast here, we get a certain length. Now, if my ruler was smaller, it could really get into the crevices and all these little types of shapes here that are not even visible on this map that the coast has. And so the smaller my ruler, the longer my object seemed to become, the longer is the length that I get. And so it almost is empirically, if you were to do that to infinity, let's say I have a ruler that with a length that goes to 0, you could almost get, if you just apply that, you could almost get that my size just goes to infinity, which of course it can't be. Because Britain isn't really a fractal, it's only a fractal over a certain range, and so you can't really have an infinite size. So what we're going to do today, we're going to actually measure the coasts of England. So,
Can I say one thing real quick?
yeah.
Notice this property is really special for fractals. It's not true in general that if you take an object and you make the ruler smaller and smaller, you'll get a longer and longer length. In fact, that's exactly what you do to measure the length of a curve in calculus. You take a limit as the little piece goes to 0, and you get a finite length. So it's a special property of these fractal-like things, not a general property of making the ruler shorter.
And we're going to talk about it more mathematically later. This is just like an example. So here are my little rulers. I'm going to pass, can you pass them on? Everyone take like a little piece of paper. And there is more here if you guys need to. And go to England on the map. And we're going to, what I want you guys to do is each of you guys should pick like sort of a zoom in measure.
One or just each group? Each group, I didn't grab one. I didn't grab one.
Maybe we
So
should,
I hope I have enough. We have
maybe
more.
we should assign them so we have full range.
Oh, a full range
Yeah, count off.
of zoomed in.
Yeah.
Okay.
Here's,
I got 14.5 at 100 kilometers.
okay.
You're at
We got 13 point.
We wanted a number of ruler lengths, and then, so 13.5 ruler lengths for what was the length? For 100, okay.
I'm only off by.
For 20 kilometers,
Yeah, we got
53.
Okay,
I had 200 kilometers and I used the longer side, so I got 3.
okay.
Yeah. I did 100 kilometers, but with the longer side, so I got 4.5.
Okay.
Andy.
57 times.
We had 50 kilometers and we got 20.
Yeah, you got
Okay.
We had 20 kilometers and we got about 90 rulers, which equals 6,400 kilometers.
You had 10. You were at 10.
We're at 20.
20. I'm sorry, what was yours again?
Ours was 20.
You were at 20 kilometers?
No, we were at 50 kilometers.
We were at 50 kilometers.
50 kilometers and 20 length.
20.
Okay. Go ahead and expand that.
But this ruler was actually a bunch.
Yeah, click on that and then just drag this over down. You see what I'm saying? Alright, 1 second, we'll have, we'll find out if we got a good power line.
Yeah, that's what I was confused. So,
But basically, before we do that, it's
You see what
if we measured it. So what do we see happening though? If we measured it at different, so the people who measured it at a 20 kilometer scale got many more got many more lengths of the same ruler. Basically, everyone was measuring with the same ruler, right? Putting the ruler up and down. And if they zoomed in, they got like 90 measurements versus the 13.5 measurements with the same ruler for the coast. So that's that was what.
Nothing, sorry.
That was what Mandelbrot, one of the main ideas of Mandelbrot's in the paper was also, and that's what we were talking about, that if you, changing the size of the ruler, decreasing the size of the ruler increases the size of the coast that you get.
Okay, so
This is a log.
This is a log plot, okay? So we didn't do the best job of measuring because we have so what we've done here is plotted a linear fit of this, and then we look at the slope, and the slope says 2.3, okay? So usually we would have expected something between 1 and 2. So when Mandelbrot measured the coastline, the west coastline of Great Britain, he got a fractal dimension of 1.25. When we did this earlier, we got.
He's French, he probably wanted to underestimate it.
I know, we are.
Although when we
We
did
have
this,
a perfect line here, you guys.
when we did this before, we got 2.4, okay? So, an explanation for why the fractal dimension is greater than 2 will come later. Unless you... I think...
No, I see it should be less than 2 because it's a line, right?
Right, because...
Yeah. So it should be less, it should be between 1 and 2, so
But there are subtleties by the way that we did this that could explain that. We have to think about this a little bit more.
yeah, so what happens is if you actually, we just realized that if you zoom in on the map, the 50 kilometers kind of changes dimension a little bit. So there was some noise in the data that.
There's also some noise because you guys have different screen sizes.
Were these
You
the
guys have
number
some-
of segments
Also misunderstood.
So what we
that
plotted...
you plotted?
what we-
Yeah, so the number of segments,
But really, it should be the total number times the scale.
Yeah.
Yeah.
That should
We
be
assumed
It
what,
shouldn't make a difference. So if you do those two, you'll get the same slope. Because all you're doing is multiplying it by a constant, right?
no, because the scale goes up. Each time you multiply the map by twice, make it twice as large, your ruler becomes half as large in length.
Right, but if we're graphing the length of the ruler size versus the number of ruler lengths.
But we didn't tell them what we were graphing.
Okay, I'm sorry, that's what we're graphing.
And I'm saying if you graph the length of the ruler, or the number of the length of the ruler, which is the magnification,
Yes.
versus the length of the circumference, let's call it.
Yes.
so number
Then-
of rulers.
Well, not the number, because the number, every time you multiply it up,
He wants the actual length. You got the actual length versus the
the
zoom scale.
magnification. Then I think you'd shift it down, maybe, or up.
During class, we'll take a look at that.
Sorry.
But basically, we did see the same thing. Everyone measured with the same ruler and got different measurements based on scale. That translates into the fact that your rulers actually had different lengths because you were zoomed in at the different levels. We're measuring the same surface. And the more zoomed in you were, the longer you found the coastline to be.
But that would happen even if it were Mandelbrot. Because if you double this, if you magnify it by a factor of 2, you get twice as many rulers around, right?
Not if you also change the size of the ruler, which
But
we
we
did.
didn't. We got the ruler at
We
exact.
did by magnifying.
But hold on, I have a question. I marked on my paper,
Yeah.
I mean, I put it against the scale bar.
Yeah.
I marked the size.
No, that, we just wanted based on your, like, everyone had equal rulers.
Oh, I see.
Yeah, so it's not related to the scale, like the actual
But I
scale, you
think
just
that's-
zoomed into different scales.
But I think that, I mean,
That'll be the.
I would think that's a better way to do it.
Well, it's a different.
Because otherwise, it then even screen size comes into issue, everything, but this gets rid of that.
These different ways of doing it just give you a slightly different
Yeah,
noise,
that's
which doesn't really shouldn't affect the power law too much.
Each way.
Yeah, that's true.
Um,
So in any case, my number should be greatly reduced by probably a factor of 7.
Can we, Juan, could you write up what we were actually plotting, like what?
I'm gonna actually come back to this.
Okay.
So this was just an example to give you guys a taste. We actually computed a fractal dimension with what we just did, but now we're gonna actually talk about what fractal dimension is. So, so we're gonna talk about dimensions today, and I actually kept, you know, throughout the class, I kept referring to, oh, we have this like one-dimensional system. We have this two-dimensional system. I kept using this word dimension quite a lot, right? But what is the dimension of an object? Like we never really defined that. And if you have, for example, if you have a familiar object like a curve or a straight line, what is its dimension?
Well, didn't we talk about it as that was like one dimension because it's the number of dimensions that you need on like an axis in order to plot the
Exactly, yes. So for example here, so what is the dimension of a line?
one.
1. So if you were to think it, we can also just think it this way, like how many points would you need in order to describe a given point in that object? So for example, if I want to describe a given point on this line, let's say I pick a reference at 0 or anywhere else, I pick any reference point. It doesn't even have to have a value, it just can be any reference point. With just one number, based on the length to the reference point, I can describe the location at every point in this line. Now, for example, if I have a square, now in a two-dimensional space, I have a square. How many points do I need to describe a given point in this object? I need 2 points now, right? Because I need its x-coordinate and its y-coordinate, given that, again, I pick a reference point, let's say at 0, 0 here. And so further on, if we have a cube, a solid, that's a 3-dimension because you need this three-dimensional set. Now, let's look at what is called the von Koch curve. The way the von Koch curve is created is through an iterative process. First we have a line. This is my S0 set. Then what we do is we divide this line into 3 segments, and we take the equilateral triangle corresponding to the middle one, and we delete this one. So S1 now will be this set. This is S1. And if we keep doing that, this little piece now is transformed for every line. This little piece is transformed into this. So whenever we have a line, this is what we see. Now, this is again a line. I'm going to do the same thing. This is a line. I'm going to do the same thing. And this is a line. I'm going to do the same thing. Does everyone understand the iterative process that we have here? And we keep doing this. And we keep doing this, and we keep doing this. I'm not going to show you right now, but if you look for the von Koch curve, so this is an example of a mathematical fractal. This little piece here just becomes really, it starts becoming very rough and rugged, right? So you can imagine it, because now these little pieces, this becomes this, right? This little piece here, this little piece again becomes the exact same thing, and so on. And then here things start getting complicated. So you have this process, and if you repeat this process up to S infinity, this is what's called the von Koch curve, the limiting set of this process. Now, what do you guys think is the dimension? Let me just pull it up also really quickly so you guys can visualize it. What do you think is the dimension of this set? Does anyone have any guesses? It's between 1 and 2. Between 1 and 2. Why?
Maybe if you did the reading, because it's not a line, but it's not an area either. It doesn't have area.
So this
It
is
can't
sort
quite
of
be
what
too
it starts to look like, right? Do you guys see that? Yeah. So this is our von Koch curve, and if we zoom in to multiple dimension, you can also get like pretty little triangles like this. But this is the picture that you start getting when you start iterating these different curves. Can you guys see it, or should I pull? Okay. But why doesn't it have one dimension, for example? Because it is a curve. It is, you have this line, and you keep putting lines in between. Why is it not one dimensional if you keep having this line?
Because it's sort of a line of infinite length.
Exactly. So it can be proven that any 2 points that you get on the surface at S infinity, because you keep adding, with each iteration process, you keep adding to it, the distance between any 2 points is actually infinity. Because at every process, this limiting set, it's really hard to, you can only visualize it up to a certain iteration. But when we talk about the limiting set, it's really you know, for any set that you can visualize it, you can actually go further and every line split it just like that and redo the iteration process. So let's see if we can actually put a more concrete number on it. So if let's say S0 had a size of L0, for example, what would be the length of S1?
Like 4/3 L0.
This is 4/3 L0. What about S2?
4/3 times 4/3 L0.
Yes. Why? Because basically you apply the same process for each line, so it's a multiplication, and it's the same process as this process, right? So it's 4/3 to the square L0, and so on. So then, for any given Sn, the length of it would be 4/3 to the n L0. Right? So it can't really be one-dimensional, and it's not an area, it's not two-dimensional, so it should be between 1 and 2. But what does this mean, really? Like, this doesn't tell us much. So mathematicians have introduced different ways of computing and different measures when they deal with fractal structures like this, which, as Mandelbrot was talking about, like, have these self-similar structures and have this roughness going on. And so one of the dimensions that they introduced is based on the self-similarity structure that they have. They take advantage of this property. And so one way to take advantage of this property, let's say, to demonstrate it, let's say we have this square, and we want to know if you scale it by a factor of 2, how many squares would take to fill up the whole thing. So you scale it by a factor of 2. R is the scaling factor. How many squares would take to fill out my whole square? 4, right? 4 copies. Now, let's say I have a cube. I don't know how to draw. Okay. How many, if I, again, scale it by a factor of 3, like scale it in each direction. How many would I need to fill up a whole one?
You're changing each line.
Yeah, so I
each
divide
axis.
each by a half.
I feel I'm
Would-
confused now.
Yeah.
Is the scaling factor in that case, wouldn't that be 2?
2. Oh, sorry.
Oh.
Did I? Yeah. Two. Yeah, sorry.
So we need you're dividing or you're increasing?
So let's say I take my cube, I take my little cube, and I make a smaller, I make a cube so if my cube has, this is my cube and this is x, for example, my new cube has x over 2 on all sides.
So is that x over 8?
Yeah.
So it's gonna be 64? No.
It's going to be 8, right?
8, that's right.
8 cubes.
Is it 8?
Yeah.
Why? Because now, so in this, every side can be separated, and you can do the same thing, but you also have to take into account the height, right?
Right.
So basically, you do this everything, but you cut here also. So now you have 4 here and 4 here, right? So it's gonna be 8. So here, which is 2 to the third. This is 2 to the second. So there is this, like, we notice that, for example, for this two-dimensional, as we used to call it, like two-dimensional objects in Euclidean space, you know, you have this sort of the dimension that you need, the power that you need to put sort of the scaled up version is somehow related to the dimension in which we find ourselves. If we add another dimension, now we have that reflected in the exponent there. So we saw that it was 2 to the third. So the connection, this connection between exponents and dimension suggests the new definition that we're going to use. And the definition is that, let's say you have a self-similar set that is composed of m copies of itself. Scaled down by a factor of r. So again, in the definition, we have something that's self-similar. This is very important, and you can scale it down to sets that are identical by different factors, which we saw before. And the similarity dimension d is just the exponent of r when we equal it to m. So in other words, d, if we take logarithms on both sides, we would have d logarithm, any base really, of r equals logarithm of m. And so d equals ln m over ln r. And this is a definition that was introduced exactly to reflect the self-similarity that we see in this curve. So now why don't we again make some groups, and let's try together to determine d for our von Koch curve. Or should we did you guys sort of get it? Or we can do an example together and then try to do an exercise. Would that be better? Okay. So if we do an example, so any factor, let's say we have our let's take any s here and scale it down by a factor. So let's say we take s0. The way we do it, pick a factor to scale. You know, here, in order to really figure out what was going on, we just picked a random factor to scale. If we would have picked another factor here, r equals 3, we would have found that we needed 3 to the second equals 9 copies. Because if you have your square again and you divide it by 3, we have 9 copies. So really the factor to scale by doesn't really matter that much because the d is kept constant here. It's 3 to the second or it's 2 to the second depending on your factor. So for my von Koch curve, I'm going to pick a factor to scale by, let's say a factor of 3. And I'm going to ask myself how many pieces, so if of the 1/3 of it, how many pieces is it made of? And we can do it and we can see it's the same number if we go through the iteration. So of 1/3 of it, how many pieces is this made of? So you take 1/3 of S0. How many of these pieces
4.
get into S1? 4, right? Because you have this piece and you put it 4 times, right? So you have 4 pieces here. What about, and going through iteratively to the process, it's the same thing because for S1, a factor of third, well, for S1, if we have a factor of 4, will now be 3 pieces and so on. So 4 pieces. So basically, this is actually kept, so m equals 4, for r equals 3. So if we plug it in here, we get d equals 4 over L3. And this is between 1 and 2, actually. We've proven it's between 1 and 2. It's actually 1.23. So let's try to do that together. Let's see if you guys can do it with a different set, which is also very important, and it's called the Cantor set. So the Cantor set, I'm going to leave the definition here actually. So the Cantor set is another famous example of a mathematical fractal where, let's say, you have S1 is again a line. And what you do is you go and you delete a third of this line, the middle third of the line. So this is S2. Again, what you do is you take these, you delete them, you delete the middle third, this is S3. And go through the process, and you'll get these sort of different points separated in different, this is S. This is called, the limiting set is called the Cantor set. Can you guys now try, so pick a certain reducing factor. And I would suggest you pick again a reducing factor is 3, because again, as we saw, this is the simplest one, because when we construct it, we take a third of it and we delete it. We take a third of it and we delete it. Here we took a third of it, right? And we added basically 2 of them extra. Can you guys now work in groups and try to get the dimension D for the Cantor set?
Because that one.
The scaling factor is 3.
No, I think it's 1.
We were plotting the whole thing.
Although should we go in the other
You're
direction?
plotting, it's
We're gonna get
point
like
scale, your scale is proportional to the size of the ruler.
So you can need
Maybe it does have
many?
dimensions.
In this case,
So let's say we do the first one. Divide in 3, you have 2 of those.
It's fractals,
So then it's log, right?
no.
So I'm just going to rephrase it really quick.
log of 2 or 3.
So think about it this way. How
The
many
same thing we're doing, right?
of itself is it composed of your measurement is it composed of when you scale it by a factor of 3, right? How many pieces is it?
We need to scale it by the factor.
Is that what you use most in your program?
Depends on what I'm doing.
There's it's 1 minus the thing.
You can probably look up Cantor set.
Thank you.
Scale it by factor of 3.
But I'm not.
So 1 goes to
Do we
3.
get the minus sign right? So it's 1 minus d equals, was it negative 2? It was negative.
Because 1 goes to 3. And then how many copies of itself? The middle third is gone. So we have 2. Like using right? Length 2. But then in the next one, then in each one of those is going to be a third missing. So we're going to have like 1.
You did more than the skill, right?
Oana?
Yeah, I'm confused.
There should
What
be
do
d
you
minus
need exactly by scale by a
So
factor?
we had 1, and then it was a 1.
Oh, sorry. Sorry, this is different.
But then, the question is,
Scaling by factor of 2,
scale by factor
right, and then when you're taking
because
that
it's just 1, so it's 1
on
solid.
each direction. Here
But
when I
then
say
of the
scale by
next
factor of 2,
iteration,
but you're going to take a third of it, right? How many of a third of it does it contain?
How many of us?
Step, and then you do the limiting sort of.
I think we got 2, 4, 6. It's like 6 over.
Yeah, 1, 3.
That's not confused, but I still think it's 2 thirds because that's a funny way to think about it.
Let's forget the rules for logarithms. Log of a minus b.
Yeah,
I'm almost
so
done
if we
with
start
spreadsheet.
So it's basically you have division, you subtract them.
If we start with
So why
1,
is it log
and
negative
then
1?
she, so call this units,
The same thing.
Yeah.
and then she said scale by factor of 3. So then that's 3. Right.
What do you done?
And then at the next iteration,
Oh,
then the question is, what is sort of, what goes in line?
I guess that's a rule.
So like we can
What goes in
It
I
must
think
be.
the rules, maybe it doesn't mean like causing negative versus.
That's not what you were
What if you reverse things?
Yeah.
I don't know.
I don't know. I think the question is it like math or is it like?
I derived it.
Yeah.
Based on how I derived it, I did the same way we did it.
But in case the total ratio.
We must have to go back.
I got
This is my
What is
This
this?
be like,
If you do it,
No, because
It's not addition.
oh, it must be log of 8.
We had 2/3.
I was,
This is 1/3.
it's log of 8 over b, it's log of 8 minus log of 8.
And then we have 3
Oh.
1/3. So we have 2 1/3 and 3. So there's 3 times 2/3.
So there's no way
And then
to
there's 3
reduce that into a single.
So the ratio is 2/3 divided by 3.
Does anyone want to volunteer to help me do it at the board?
So when we
Or like, what numbers is that again?
it's like
Yeah.
3 and you just divide it by
Right. So I exactly. So really, the whole point is that you
Yes.
need to actually scale the whole thing up. You just sort of collect
Do you want to come help me do it at the board?
I mean, all I did was like, I figured out that M was
It's not easy.
and I wrote a LM here
Yeah,
because
but
we know the total
You
length
can
changes
walk us
as
through
you
your
change
thought
the
process,
rules.
because
So
I
we
think some
expect
people have.
as you roll it bigger,
Okay.
to decrease.
Okay, you can do it from there.
Proportional to m to the minus.
Yeah.
So since we're dividing into 3 pieces, R is 3, and then since every component is being turned down into like 2 components of itself, M is 2, so you just go ln2 over ln3.
For this, for the first situation, right? You can, it doesn't really matter, the interesting thing is it does not really matter which situation you choose. And I'm gonna show you that in a minute, based on, I mean, you can just choose a different scaling factor, right? So just like we did with this picture, right? We picked something smaller and we asked how many times does it fill, like something that's similar to it. How many times do you need to plot it in here to fill the whole thing? And it turned out to be 4, right? Here, I just choose to pick this one, right? A third of my initial line. How many times do I need to put it in my S2? 2 times, right? So M equals 2, and R equals, I picked a third of it, right? So my factor was 3, so that's why I got ln2 over ln3. I can also do it with the next situation. For example, if I pick basically a third of this one here, let's say, this is a third of this line here to be my scaling factor. I have, how many here do I have? I have 1, 2, 3, 1, 2, 3, right? So I have 6 of them. And then how many do I have here? 1, 2, 3, 4. I have 4 of them. And so I have ln4 over ln6, which is actually equal, it's just a multiplication by a factor of 2, basically. So these two are equal. So,
Are you thinking ln4 over ln9?
Yeah, I think
Yeah.
9.
1, 2, 3, 4. And I pick, this is a third, so I delete the second. This is a third of this one, right? 1, 2, 3, 4, 5, 6.
But you got the middle portion that isn't sent by line. You still have to scale it down because it's there. So that's another 1, 2, 3.
Oh, because it's a third of my initial. Yes, you're right. So that's how you get it for the Cantor set. And this turns out to be 0.63, which is actually smaller than 1. So this has, the Cantor set has a smaller dimension than 1, and it's satisfied, I really wanted to mention to you guys these 2 properties that it satisfies, because we're going to come back to these properties. The geometric, there are a lot of objects that are fractal-like, and that maybe don't have a fractal geometry, but they're fractal in this topological sense that has these 2 properties that the Cantor set has. And I really wanted to mention to you guys, first of all, it's disconnected. And what it means is that it contains no interval inside of it. So there are no connected points inside of it, inside of my limiting Cantor set S infinity. So every point is disconnected from any other point. There's no interval of points. And two, it also contains no isolated points. In the sense that for every point that I choose in my Cantor set, there exists a small enough vicinity such that, and for any vicinity around it, there exists another point. This is my x0. There exists another point x close enough to it such that x is within epsilon distance of my x0. So these can be quite maybe difficult to understand intuitively. So this tells me that in my Cantor set that you have all these points eventually, so you repeat this process and you have all these points that are separated by distances of different lengths, right? You have these two almost contradictory properties of it that you really have no interval. So every point is disconnected from any other point. However, every point is also sufficiently close to other points around it. So they're near any point that I pick in my Cantor set, and for whatever vicinity that I pick that is larger strictly than 0, there are other points. There's at least another point in that vicinity that's close to my point. And this is what, so this is called topologically, this is a topologically fractal set. And I'm going to come back to this type of topological understanding of these points that are sort of far apart. They're not connected to each other. There are gaps. Between every 2 points there's a gap, but the gaps are always, sufficiently, so you can always find sufficiently small enough gaps. Yeah.
There are going to be an infinite number of points. The true distance is going to be limited by the inertial line, correct?
My L0, so between them, yes.
And similarly, so doesn't that also mean that there will be an infinite number of points within each distance from one point?
Yes, you're
okay.
right. Yeah. So this just says,
I
no 2
realize
points are
that's just
connected. It
a
doesn't
thought.
contradict. Yeah. No 2 points are connected, and you can also find points that are sufficiently close. Of course, you can also find points that are.
But I mean, there'll be an infinite number of points.
There'll be an infinite number of
within that
points.
sufficient closeness.
There'll be
Just
an
as an
infinite number of
interesting
points.
side point.
And I think, yeah, exactly. There'll be an infinite number of points, and they're all, yes, indeed, they're all like within this restricted region of my, basically, if I want to have my line, right? This, within the certain length, which comes
But
back
even
again,
within
takes
the
us.
very small length.
Even within the very
yeah.
small, yeah.
Yeah, okay, thank you.
And which takes us back again to that packaging economy, right? Like I have these points, but they're all within this length, yet, and they're very packed together, right?
What about the edges? Aren't the last points isolated?
Yeah. The last points are not isolated because they have points. So, for example, you're saying, oh, is this point not isolated? Well, it has points this way.
It's isolated in one direction.
It's very isolated in one direction here, but it has any point has sufficiently, and the same thing is true for the points here. So it's very important, and we're going to come back a little bit to these topological properties because it's very similar to what happens on our strange attractors, and I'm going to just make a brief point of that towards the end of the class. But another dimension, I wanted to mention another dimension that people used and that I want you guys to be familiar with. Let's take a 7-minute break and then let's get started again so that I want to make sure you guys we finish early. So And I just have, before we go into like talking about the paper and again about the map that we saw, we want to go back to our power law. I just wanted to connect it a little bit to the strange attractors that we talked about last time, because some interesting properties and why a lot of you guys can read a little bit more about it on your own, but like why it's said that strange attractors have this fractal microstructure is that they satisfied these two topological, like if you let the trajectories run enough, or if you start, it's the same thing with starting different trajectories and you let sort of the strange attractor fill with enough points. You can see that they sort of have this sort of fractal structure to them, and one way to compute dimension in that case, and we're going to talk a little bit, because we saw the Lorentz attractor last time, so one way to compute, another way to compute dimension is for these set of points. So you have your, let's say, space here. Another dimension is, let's say this is my point X on my surface, on my strange attractor, on my fractal, and you have all these other points around it. And so if we let nx of epsilon denote the number of points within vicinity epsilon of
what we'd expect is we expect that as the scale gets bigger, so we make our ruler bigger and bigger and bigger, the total length of the coast, should it get smaller or should it get bigger?
Smaller.
Should get smaller, right? So we know that this thing has to scale with s to some power, and so let me just write that, s to some power, that's negative, so alpha here is positive. But the way it's typically written is like this. It's written as 1 minus d. This thing is the fractal dimension. This d. So if the fractal dimension is exactly 1, this is s to the 0, and therefore L is independent of s. So d equals 1 is the case, is not a fractal. It's smooth. And d bigger than 1 is a fractal. And really I should say, to make this a little bit more exact, to say that d has to not only be bigger than 1, but it has to be less than 2. Okay, so any questions about that? So why does the fractal dimension have to be less than 2? Anybody? We haven't talked about this a whole lot, but maybe you can take a guess.
Because then the length of the object starts to take up area, basically.
Yeah, so we'd expect that if L, things that scale like s to the minus 2 are scaling like an area. And we're expecting this thing to be some sort of a length. So if you think about a line as being a dimension 1, which you all learned a long time ago, and a two-dimensional object is being dimension 2, so a shape, something with area is being dimension 2, then a fractal is in between.
But I just want to make sure, you're just referring basically to like that particular example, because we just saw the Cantor set that had a fractal dimension less than 1, right? So it's not necessarily, you're referring to, we had the coastline, which is sort of a curve, like which is a line, but you can have fractal dimensions less than 1. So this is not the whole, like.
But for the Cantor set, though, it makes sense that the dimension should be between 0 and 1, because
right.
What's a dimension of 0? A
Point.
point, and a dimension of 1 is a line, and you can see from the Cantor set that it's not points, it's more than points, because a single point would just be a single point, but it's less than a line. When you draw it out, you don't have a full line, and so it makes sense that that should be, so
Yeah.
Thinking
So
about
we
it this
talked
way
a
gives
little
you
bit like with some people
Wait, the
here.
Tanner is a super log, isn't it?
No, so we talked a little bit. I don't for people who are around here in the break, but I can repeat. So what could you like intuitively
Wait,
think a little bit
Cantor.
of these dimensions? So we had the von Koch curve and we had the Cantor set, right?
Okay.
The Cantor set was the set of points,
Okay,
right?
yeah.
Right. And so it's like it's not like the fact that you don't have any segment in there makes it have dimension less than 1. So it's like you have an intuitive feeling that it's between 0 and 1. And then from the von Koch curve, it's all of these lines connected, but it has no area. So you have this like intuitive feeling, it's like it's between 1 and 2. So we just want to make sure this is like,
Yeah.
so we're referring to the coastline example where you have this sort of like lines that are fractal-like, and it's not a set of points. It's not. You can have any type. Like the list that I'll show you can have a lot of different fractal dimensions.
Yeah, that's a good point. So in this particular case, this type of fractal we're looking at, expected to be between 1 and 2. But in general, a fractal is something that has a fractional dimension, hence the name fractal. Okay, so now what do we do? What Marshall actually plotted was he plotted the number of ruler lengths versus 1 over the scale. So he plotted this. He plotted n as a function of 1 over s. So we can write that down. Just doing some algebra to this equation over here. You get, do I want to, yeah, I guess I'll do that. So you get this, and you get this. So you get L over this little L, this is just some scaling, some constant, remember, and then 1 over S. So I'm going to now combine this L of S with this 1 over S here. And I get S to the 1 minus D over S. And I'm just going to write proportional to now, because there's just some constant out front. And this thing is equal to S to the minus D, which is equal to 1 over S to the D. So the equation we have is that n as a function of 1 over S should be equal to some constant, which in this case is 1 over L, but I'm just going to write C for a constant, times 1 over S to the D. Okay. And now there's one last step. And the thing that he plotted was a log-log plot. Now all that means is you plot on the x-axis log of 1 over the scale. And on the y-axis you plot log of the number of ruler lengths, and you get some function. And let's see what we get here. I can take the logarithm of both sides. And I get log of n equals, the constant out here is going to end up being something like this. And I get this. So take a look at that, think about it for a second, make sure you know what algebra I did. I did 2 steps in 1 here. Typically you write this as log of 1 over s to the d power, and you can pull the power outside of the logarithm. It's just a rule of logarithms, if you forget.
And really, if we think about what we did before, right? You had it's very similar. It's basically the same thing as we did before. You had your little. This is like m equals 4 for r equals 2, m equals 9 for r equals 3. It's really the same thing. You plot basically log of r and log of m here, right? So we saw that relationship of between log m and log r there, right? So it's just think about what we also did before.
So anytime you plot we're going to talk a lot more about these log plots next week, because when we talk about power laws, we're going to be focusing on log plots. So if this is unfamiliar, don't worry about it. We'll talk about it again. But in general, what we've done here is by plotting log versus log, this is like our y component now, log n, and this is our x component, log 1 over s, so we have y equals some constant times x plus some other constant. That's a line. So we plot a log-log plot, and we find a line with a slope of d, our fractal dimension. That's what we did then. Once we look at the line with all the data that you guys took, we get the slope, and it tells us immediately our fractal dimension. So Marshall's going to come up here again and show you guys the plot with the scaling factor. If we have time, actually. Do we have time? What time is this?
It's the line won't change. So the reason that we got 2.4 is because I accidentally plotted the log versus the natural log of the two variables.
Classic mistake.
And because I was looking at it to see if you do the log plot versus if you do the natural log plot and see if that makes a difference. So that's why we got what we did. So when you plot it correctly and actually do the log instead of the log natural log, you get a slope of 1.01, okay, which fits our description of being between 1 and 2.
Just barely.
When I did this earlier, I got a slope of 1.04. Other people have measured different coastlines, so when people measure the coastline of Africa, they get a fractal dimension of about 1.02. When Mandelbrot did the west coast of Great Britain, he got 1.25, and kind of depending on where you are and what coastline you're looking at, that fractal dimension will change.
But does that say it's very close to a non-fractal, which is 1?
It says, yeah, it does. It says in some sense that what we've measured is very close to a non-fractal. And I don't know what the real number would be if you did this very carefully for the coastline. There's some error in there.
1.25?
That's just for the west coastline of
Is
Britain.
it for the west? I thought it was for.
We did the whole thing, so it might be a little bit different. But yeah, it's probably closer to 1.2 than 1 in reality. But we have some error in our measurements. Some of you guys sort of had different screen sizes, did something slightly different than each other. And on top of that, it's dependent on the zoom. If you stay zoomed out so you never really see the fractalness, you're going to get something close to 1. If you zoom in enough so that you can really see the fractalness, you'll get something that's closer to the real fractal dimension. To really do this incredibly accurately, you'd want to plot this over a large range of rulers, scales, and you'd want them to be separated by orders of magnitude. And we sort of did, we did a couple of orders of magnitude, but you'd really want to do, 8 orders of magnitude. 3 or 4 orders of magnitude, whatever you can actually do with a map to get the most accurate measurement.
Yeah. So just think of these, you have these log plots, and you get this slope, and the d is what gives you the dimension. And if you can, you should go home and go back to our lecture and look as we, for different types of fractals, this M and R, and try to maybe plot for different of those, for the Cantor set, for example, try to plot this d, try to plot that function and try to get, see that it's exactly log 2 over log 3.
I just want to say one other thing, which will help you guys for next week, and it's a good lead into next week. And that is, this was pretty nice, because we got a line. We plotted a log, and we got a line, so we could actually measure the slope really nice and easily. So the question is this a special property of fractals? Is it a special property of the type of function we have? Why did we get a line? Why was it so simple? And this type of a function here, something where you have some function is equal to some constant times x to the nth power, where n is also a constant, is called a power line. So the most basic example of this is a parabola, y equals x squared. That's a power line. Or even simpler example is a line, y equals x. And if you take the log of both sides of this, just like I did before, you get a line. So anytime you have a power law, and you plot it in log form, you get a line. And it tells you the power. The slope is just the power. So we're going to talk a lot more, this is useful for fractals because you often deal with power laws. Next week we're going to talk more about power laws and what other things we expect to give us power law relationships. And to do that we're going to be looking a lot more at log plots, and in particular log plots that show linear functions.
It's a bit more than classical papers, so it's influential, that's why we chose to discuss about it, but computer algorithms are evolving fast, so things that they are predicting are very much used in compression of images.
They use it in movies a lot today too, because this roughness that he was talking also in the TED video, you can really put different dimensions and control, for example, when you go into, like, you try to do clouds or you try to do mountains, you know, like you can control putting different dimensions for these fractals. You can control like the roughness of the landscapes, basically.
So it's been zooming in, you guys saw it zooming in, but it looks very different now. It looks like we're just gonna zoom into this part over here and it's gonna be some little blob and we'll be done. So if that was true, it wouldn't be a fractal. This is the cool part.
Do you guys start seeing the self-similarity too? Because like we sort of come back to the same type of shape that we left from.
Yeah, exactly. So remember, we started with this sort of shape and we zoomed into one of these little branches, and now we see the shape again. So this is always a fun thing to watch for hours on end on a Friday night.
Add some music.
Maybe some music, yeah. Maybe a few.
I had the Bach variations that we had last time. Relaxing.
What's the dimension of that Mandelbrot stuff?
I don't know.
Should be on your list.
It's on my list, yeah. I actually don't know. It's
Any guesses?
Less than 2.
Or do the one.
It's blowing your guys' mind. Yeah.
And it's actually a really, like, if you guys read about it, it's such a simple iterative process that it comes from. Basically, we're out of time, but I'm just going to tell you guys really quick. So it basically comes from this map. So the iterative process, Cn plus C. So for any point C in the plane, you pick a complex number C in the plane, and you start with C0 equals 0, and then you go through this iterative process. If this equation has a solution that doesn't go to infinity, it's black on the Mandelbrot set. And then the other colors come from how fast the points that are not black go to infinity. So basically, C for every point in the plane here, it's mapped to one of those C's, and if that solution has if that equation iteratively, so you start from Z0 equals 0, and then Z1. Oh, actually, it's squared. Sorry. Yeah, it's squared. It's not. Yeah, it's squared. Z1 equals Z0 squared plus C, so equals C. Z2 equals C squared plus C, and so on. And if this has a sort of a finite, if you don't go to infinity here, then it's colored. It's a black point in this plot.
How do you measure how fast you go to infinity?
There are complicated ways to measure it. I mean,
Okay.
even like if you go, like just a very simple example, if you go on a line versus on an exponential, exponential is faster, right?
So
I don't really know how they put the colors here, but the darker the colors, the slower. The lighter the colors, the faster.
But it would be relatively straightforward to make a black and white invalid or something.
Yeah, it would be if you don't put the colors, yeah. But I think the colors even are pretty straightforward, but I'm not really sure how they do it.
Okay.
Cool, thank you guys, and I'll see you next time.